Welcome to the next lecture on wireless communications. Today we will talk about coding techniques for mobile communications. Let us have the brief outline for today's talk. We will briefly summarize what we have learnt so far, followed by a brief description of linear block codes. We will then look at Galois field theory and then have a small introduction to cyclic codes. So, this is the outline for today's talk. First, a brief recap. We have previously looked at various kinds of equalization techniques for mitigating the effects of multipath fading. We looked at linear equalizers followed by a set of nonlinear equalizers. Specifically, we talked about decision feedback equalizer, maximum likelihood symbol detection, maximum likelihood sequence estimation. Then we moved over to the various algorithms for adaptive equalization, namely the zero forcing, the least mean square and the recursive least square algorithms. We then looked at various kinds of diversity techniques: space diversity, polarization diversity, frequency diversity, and finally time diversity. So, we realized that out of the three important techniques to overcome the effects of bad fading channels, the two are equalization and diversity. The third one is coding, specifically channel coding. Today we would like to have a brief outlay of the channel coding techniques for mobile communications. So, within this description we will talk about linear block codes, Galois field and cyclic codes. Now, what are error control codes or error correcting codes? Error correcting codes are used for correcting errors when the messages are transmitted over a noisy channel or stored data is retrieved. So, we know that error control coding is used for mobile communications, but if you store your data on CD, there also we use error control coding. The noise that we are talking about could be thermal noise, or it can be caused by lightning, human errors, equipment malfunction, voltage surge, or any other thing. So, any of these things can cause noise. On top of that, if you are working in a fading channel, you will get burst errors when you pass through long durations of fade. To detect and correct errors, we use error control coding, which is also known as channel coding. Now, what is the basic idea behind channel coding? The basic idea is to add a certain amount of redundancy to the message prior to its transmission through the noisy channel. However, this redundancy is added in a known fashion. This redundancy, which is basically some extra symbols, as I said, is always added in a known fashion, which is known to us, the transmitter and the receiver, and is unknown to the noise clearly. Let us look at an example. A lot of redundancy is present naturally in the English language. For example, if you read the following sentence, it has a lot of errors and missing letters in it. However, it is not very difficult to understand and read the sentence. Coding theory is an interesting subject. So, we have automatically corrected for errors by virtue of knowing that the English language has lot of redundancy built into it. Your coding theory, which deals with not letters but bits, works along similar lines. We have the redundancy, so we can reconstruct, that is detect and then probably correct the errors once we received an erroneous message signal. Now, let us look at the block diagram of a digital communication system with a channel encoder and decoder. So, you have an information source. Normally, it is followed by a source coder. We have taken it out from the diagram because we want to focus on the channel encoder, followed by the modulator. The signal is then passed through the channel where noise is added, and in our case this channel would most likely be a fading channel. We have the demodulator followed by the channel decoder and then the user of the information. So, this is the model that we will work with. In most cases, the channel coder and the modulator are two separate blocks. In subsequent lectures, we will see that in some cases it is possible to combine the channel coding block and the modulator together to talk about coded modulation. Example, trellis coded modulation. Now, let us define certain terms that we will use throughout our lectures. Firstly, a word is a sequence of symbols. A code is a set of vectors called code words. The Hamming weight of a code word is equal to the number of non-zero elements in the code word. So, it is just a number. The Hamming weight of a code word C is denoted by W of C. It is called the Hamming weight or simply the weight of a code word. The other term is Hamming distance. The Hamming distance between two code words is the number of places the code words differ. Again, the Hamming distance is again a number. The Hamming distance between two code words C1 and C2 is denoted by distance C1 comma C2. It is easy to see that distance between C1 and C2 is equal to the weight of the code word C1 minus C2. Okay. Clearly, Hamming weight and Hamming distance have something to do with finding out how similar or how different are two code words. If the Hamming distance is more, they are different. If the Hamming distance is less, they are more similar to each other. Let us look at an example. Let us look at the word 10110. The weight of this is 1, 2, 3 because there are only 3 non-zero elements here, the other 2 are 0. So, it should be 3 here, and the distance between these two is the number of places they are different. It is different at number 2, and then it is different at number 3, and then it is different at number 5. So, it is different at 3 places. So, it should be 3, which is correct. So, the weight is 3 and the distance is also 3. Now, let us come to a special class of error correcting codes called block codes. A block code consists of a set of fixed length code words, hence the name block codes. The block length is fixed. The fixed length of these code words is called the block length and is typically denoted by small n, lowercase n. A block code of size m defined over an alphabet with q symbols is a set of m q-ary sequences, each of length n. Please note, for binary case q will be 2, but that does not mean that block codes necessarily have to be binary. You can have non-binary block codes as well. For the special case that q is equal to 2, that is binary, the symbols are called bits and the code is said to be a binary code. Usually m is equal to q raised to the power k for some integer k, and we call such a code an n comma k code. So, basically what a block code does is takes k bits and transforms them into n bits, where n is larger than k, thereby adding n minus k redundancy. How you add those redundancy makes the difference between a good code and a not so good code. Let us go with some more definitions. The minimum distance of a code is the minimum Hamming distance between any two code words. So, as we know, a code is a set of code words. Fine. Now, amongst this set of code words, if you compare two code words at a time, some of them will have a greater Hamming distance than other pairs. The pair which gives you the minimum distance is called the minimum Hamming distance of the code. If the code C consists of a set of code words Ci, where I is equal to 0, 1 through m minus 1, then the minimum distance of the code is given by d star and is equal to minimum of distance of Ci, comma Cj, where I is not equal to j. So, different pairs of the code words within the code, the minimum distance of that is d star. Now, another term which has something to do with the efficiency of the code is called the code rate. The code rate of an n comma k code is defined as the ratio. So, it is a ratio, it has no units, it is k over n and reflects the fraction of the code word that consists of the information symbols. So, again the objective of a code which is n comma k code is to take k bits at a time and convert it into n bits. Now, k bits are the information bits and n bits are the code word bits. So, k over n, which is definitely a fraction because n is larger than k, because you add n minus k redundant bits, k over n is the code rate. It should be less than or equal to 1. Equal to 1 means you are not doing any coding at all. The closer k by n is to 1, the more efficient is the code. Let us look at an example. Let us look at a simple block code which has 4 code words. Now, look at this. The block code C can be used to represent two binary numbers as follows. So, you have uncoded bits and the corresponding code words as follows. So, if you have 0 0, you represent it like this. If you get 0 1, you represent it like this, 1 0 you represent it like this, and 1 1 you represent it like this. So, for 4 possible 2-bit inputs, you have 4 possible outputs. Here m is equal to 2 because q is equal to 2, m is equal to 4, k is equal to 2 and n is equal to 5. N is the length of the code words. Here please note n is 5 and is equal to the block length of the code. Each of the code words is of length 5. Now, suppose you have an incoming bit stream 1 0 0, 1 0 1, 0 0 1 1 and so on and so forth. Now, suppose our job is to encode this raw bit stream coming in using the following code. So, first step is to break up the sequence in groups of 2 bits, because we can only take 2 bits at a time and assign a code word to it. So, if you break it up into 2 bits, it will look like 1 0 first 2 bits, then 0 1 and then 0 1 and then 0 0 and then 1 1 and so on and so forth. Now, for 1 0 you replace 1 1 1 1 0, for 0 1 you replace 1 0 1 0 1 and so on and so forth, and so you get the following code words. Clearly, for a much shorter input bit stream, you get a much longer output bit stream. The code rate of this will be 2 over 5 k over n. So, for every 2 information bits, it is putting 3 redundant bits to form 5 code word bits. The minimum distance of this code is the minimum distance between any 2 code words. And here, if you look at it, the first code word and second code word differ only at 2 places. And if you can carry on this comparison, because there are 4 choose 2 possible pairs, which is 6. If you look at all the 6 distances, we will find that 2 is the minimum distance possible, hence d star is equal to 2. We will learn soon that d star has something to do with the number of errors the code can detect and correct. So, in some sense D star tells you how strong the code is in terms of error correcting capability. Now, let us look at a subclass of block codes called linear block codes. Now, what is the philosophy? The basic philosophy is to add more and more structure in our codes, because what noise does is breaks the structure, and if we have a good structure in place, these are mostly algebraic structures, then we will able to detect the missing links and hopefully correct the errors. So, the first constraint that we put on block codes, and constraints means more structure, is linearity, and we define something called as linear block codes. A linear code must have the following properties. The sum of two code words belonging to the code is also a valid code word belonging to the code. So, sum of two code words is also a valid code word, and of course, the all zero code word is always a valid code word. If these two conditions are satisfied, then you can say that the block code is also a linear block code. And the other property that comes is that the minimum Hamming distance between any two code words of a linear code is also equal to the minimum weight of any non-zero code words. That is, you do not have to compare all the pairs and find the distance between them. You compute the Hamming weight of each of the code words except the non-zero code word, and whichever is the minimum you take it, and it will be the W star equal to D star. So, the minimum weight of a linear code is the smallest weight of any non-zero code word and is denoted by W star. Please note that the presence of an all zero code word is a necessary, however, not a sufficient condition for linearity. So, the first thing that we must check if you are asked to verify whether a block code is linear or not is the presence of the all zero code word. If it is present, we go further, otherwise we say, look, this cannot be a linear block code. Now, it is very easy and efficient to define linear block codes by matrices. So far we have seen that linear block code is nothing but a table, which is a lookup table. So, you have input bit streams, and for any combination of k input bit streams, you have a combination of n code word bits. So, it is difficult, lengthy and more time consuming to store and recall your linear block codes in terms of lookup tables. It is much more efficient to implement them as matrices. How do we do that? So, we have the matrix description of linear block codes. We define the generator matrix G, which converts, in our parlance it is encodes, a vector of length k to a vector of length n. If we can have this magical matrix G, which can take a vector of length k and make it a vector of length n, and do it correctly for all possible k bits, then we have a generator matrix which can generate the entire code, hence the name generator matrix. Let the input vector, which is the uncoded symbols, be represented by vector I. So, boldface represents it's a vector. In that case, the coded symbols will be given simply by C is equal to I times G. So, C is a 1 cross n vector, I is a 1 cross k vector, and G is a k by n matrix. So, if you multiply 1 by k with k by n, you get 1 by n, which is C. Here C is the code word and I is the information word. The generator matrix clearly will be a k by n matrix. So, if G can truly generate your entire code, then you only need to save and store k into n bits and define the whole code word. So, your lookup table, which would have been very memory expensive, would not be required to store in that fashion. We can just store the generator matrix. Let us look at an example of a generator matrix. Consider the following generator matrix: G in the first row 101, second row 010. It is k by n, 2 by 3 matrix. So, this should be able to take 2 bits at a time and convert it into 3 bits. So, if you have the following representation, C1, if you take 00 and multiply it with the generator matrix, you will get a C1 equal to 00 times G is equal to 000. If you take the other 2 bit input 01 and multiply it with G, you get 010 and so on and so forth. So, for the 4 possible 00, 01, 10 and 11 inputs, which are 2 bit inputs, you have the 4 possible outputs. Therefore, this generator matrix generates the code 000, 010, 101 and 111. Since it is a linear block code, if we are asked to find the minimum distance of this code, it will be the minimum weight of this code, which is the number of non-zero elements in any of the non-zero vectors, either here, here or here, and clearly this one has unity 1. So, the minimum distance d star is 1. Now, we define a dual of the generator matrix called the parity check matrix. It has some interesting properties. A parity check matrix provides a simple method of detecting whether an error has occurred or not. So, the first job is to detect whether an error has occurred, and then the second step is to see whether you can really correct the error. So, the job of the parity check matrix is to detect whether an error has occurred. Let us define a matrix H such that code word times H transpose is equal to the 0 matrix. This H is your parity check matrix. So, for any valid code word, if you multiply it with the transpose of the parity check matrix, you will get a 0 matrix. This will actually be a vector 1 times n minus k. So, if it is not 0, then clearly C is not a valid code word, and hence you have detected an error, because coding is about transmitting and receiving valid code words. Since C is equal to I times G by definition, therefore, we can write I G H transpose is equal to 0. For this to hold true for all valid code words, that is I can be anything, we must have G H transpose is equal to 0, which means if you have the G matrix, which is your generator matrix, you can find out the H matrix and vice versa. Please note that for any G matrix, H matrix may not be unique. That is, you can have several H matrices which satisfy this condition. No problem, any one of those H matrices would be able to work with your C H transpose equal to 0 and will be able to tell you whether an error has occurred or not. The size of the parity check matrix is n minus k times n. So, this is the size of the parity check matrix, and for any systematic G. So, we define a systematic generator matrix G as one which can be represented in a matrix where the first part is a k by k identity matrix followed by a k by n minus k parity matrix. So, if your G has been defined as I partitioned P, then H matrix is simply minus P transpose partition I. Here I is an identity matrix of the size n minus k. Here I is the identity matrix of size k. P T represents the transpose of the matrix P. So, this tells us one way to generate an H matrix from a G matrix and vice versa. If you have the G matrix or the H matrix, you uniquely define the code. Let us look at an example. So, for a 7,4 linear block code, the generator matrix is given by the following equation. Now, please note the first k rows and k columns form an identity matrix here. So, this is of the type I partition P. So, a P matrix is k by n minus k. So, your P matrix is just the last 3 columns of the G matrix here, because it is already in the systematic form. Now, for a binary case, minus 1 is equal to 1, because 1 plus 1 is 0, binary addition, it is a modular 2 arithmetic. So, for the case of binary, we can write the parity check matrix as, again you will have the last 3 columns, the identity matrix, and this is minus P transpose. So, take this P and just transpose it, minus P transpose is P transpose, and you have your G matrix and your H matrix. So, G H transpose will be the 0 vector. Here is H is equal to minus P transpose I. Given this, you can get a G, given G, you can get the H. This format of G is called the systematic generator matrix. Now, let us come to the objective for which the error control codes were designed for: error detection and correction. So, the objective is first to see an error has happened at all or not, and then if you have detected that an error has happened, then can we correct it? If so, how many errors can we correct? So, to detect T errors per block, we must have D star, which is the minimum distance of the code, greater than or equal to T plus 1. What does it mean? It means that if my T is less than D star minus 1, I take this 1 on the other side of the inequality, then I can still detect the error, which means that if the error, the number of errors is D star, then the problem is that one of the 2 code words which form the pair for minimum distance might get changed into the other code word if you have D star errors. Any errors fewer than D star can be detected, because it will not make any code word into another code word. It takes D star changes. Since the Hamming minimum Hamming weight is D star, it requires D star changes of one code word to go and transform itself into another code word. So, D star minus 1 is the maximum errors that can be permitted, so that our detection algorithm can work. So, in order to have a detection for T errors, we must have the condition D star greater than or equal to T plus 1, T plus 1. To correct T errors per block, so we are talking about block codes, we now want to correct T errors, we must have the condition D star greater than or equal to 2T plus 1. Now, why is that? Consider the following diagram. We have the code word C1 here and code word C2 here, and they are separated by the minimum distance d star. It is a distance notion, so we have separated them here spatially. Now, if an error happens, if the number of error is 1, we will move 1 unit away from the code word, because now the Hamming distance will be 1. If there are 2, it will move further away, 3, 4 and so on and so forth, until we have d star, because d star steps will make C2 look like C1 in the worst case. Why? They are only different at d star places, because the distance between these two is d star. I am talking about the minimum distance pair code words. So, it takes d star errors to make C2 appear as C1 and vice versa. Now, let us say it is a decoding sphere, because it is distant from C3, C4, C5 other code words also. So, you can define a sphere which is called the decoding sphere. If t errors make the sphere boundary here and t errors make it here, and these two circumferences just touch each other, then we have the condition that 2t is equal to d star. In that case, the spheres will not intersect. That means t errors, if any of the t errors happen, then they can be decoded back to C2. If any of the t errors happen, the erroneous code word could be mapped back to C1 here. That is, any code word or any word appearing within the decoding sphere of C1 will be decoded as C1. Any erroneous word occurring within the sphere of C2 can be mapped back to C2. There is no ambiguity. Only in the case when the spheres intersect, we will have an ambiguity and we will not be able to correctly decode. So, in order to ensure that t errors can definitely be corrected, I must ensure that the spheres do not intersect. Now, the minimum condition required is d star is equal to 2t, and there also we have this condition that if an erroneous word is exactly t from this one and t from this one, I cannot make a decision. So, I put a safeguard and I say d star should be greater than or equal to 2t plus 1. So, if you have this condition that d star exceeds 2t plus 1, t errors can be corrected as well. Okay. So, it clearly tells us that in order to have your block code correcting more number of errors, you have to increase the d star. Now, let us talk about syndrome decoding. Suppose H our parity check matrix of an n comma k code is defined by capital H, then for any vector v which is an element of Galois field q raised by n, we will talk about Galois fields very soon, the vector S is equal to VHT is called the syndrome vector. What is S? S is nothing but V, the received word, multiplied by H transpose. Now, we have seen earlier that if this vector V were the actual valid code word C, then CH transpose is 0. So, the syndrome will be 0. In any other case, when V, the received word, is not equal to a valid code word C, you will not get a 0, you will get something. Now, if that something can point to the specific error pattern, then we are in business. That is, if this vector can be the syndrome to the disease, which is our error here, then we can actually decode it back. If there is a unique syndrome for every error that we can encounter, then we can uniquely map back and remove that error and hence do a error detection and correction. So, this S is called the syndrome of V. It is called a syndrome because it gives us the symptoms of the error, thereby helping us to diagnose the error. Now, let us take a very brief mathematical detour and talk about something called as the Galois field. This is named after a French scientist Galois, hence the pronunciation Galois. Galois field, we will realize, is something which follows a set of properties, and we need to do this because we want to move into the next domain of linear block codes, which is called the cyclic codes. Cyclic codes, we will realize, are much easier to define once we understand a little bit of Galois field theory. So, what is a field? A field F is a set of elements with two basic operations, the addition and the multiplication, and these elements of the field must satisfy the following properties. So, if you can find a set of elements which have the basic addition and multiplication defined and satisfying the following properties, you have found a field, and we will define our codes over certain fields. Normally, we should say Galois field, but in short we will just mention it as a field. We imply the same thing. So, F is closed under addition and multiplication, that is, A plus B and A times B are in F if A and B are in F. Okay. So, the resultant elements, if you do A plus B or A into B, if A and B belong to the set here, then the addition and the multiplication yields another element should also belong to the same set. For all A, B and C in the field F, the following should hold: the commutative laws, that is, A plus B is equal to B plus A times B is equal to B times A, and so on and so forth. Associative laws, A plus B bracket plus C is equal to A plus bracket B plus C, or A times B times C in a bracket is equal to bracket A dot B dot C. And then the distributive law, A times B plus C is A times B plus A times C. Further, there are two identity elements which are 0 and 1 must exist in the field F, satisfying A plus 0 is A and A times 1 is A. Then we define two more things. For any element A in the field, there must exist an additive inverse, which is an element such that A plus A minus is 0. This is called the additive inverse of A. This must exist, and for any element in A, there should be a multiplicative inverse also, such as A times A inverse multiplicative is also 1, except for 0. So, it must be that the additive inverse and multiplicative inverse must say. The above properties are true for fields with both finite as well as infinite elements. Question?
Sir, should it be A inverse?
Yeah. So, this minus 1 has shifted down, it should be A inverse, A raised to power minus 1, and here A, it is not A minus 1, it is A raised to power minus 1, which is giving you the multiplicative inverse. A field with a finite set of elements, say Q, is called the Galois field and is denoted by GFQ. So, for all practical purposes, we are considering a field of finite elements, and we will talk about Galois field GFQ. If Q is equal to 2, then we have GF2, the binary field. If only the first 7 properties mentioned here, that is, there is no multiplicative inverse, other than that all the properties are satisfied, then that set is called a ring. Okay. So, a ring with an additional property that a multiplicative inverse exists becomes a field. Fine. So, if we can ensure this, then we can define our field and a ring. Today we will learn to construct Galois fields as well. Let us now look at an example. Let us consider GF4, that means it is a Galois field with 4 elements. Let us denote these elements by 0, 1, 2 and 3. Now please note that there is nothing sacrosanct about defining it as 0, 1, 2, 3. I could have defined it as 0, 1 because 0 and 1 must exist, an apple and an orange. It still will form a set of elements. But please note that this set must follow certain rules which we have mentioned in the previous slides, and hence we should be able to construct an addition table and a multiplication table. If we have that, we will ensure that all of the properties are satisfied. So we can define a field by just defining the addition table and the multiplication table. So let us first look at the addition table. So clearly, if you add something with the 0, you get back the same elements. So these two rows and columns are fixed, and then you have, for example, 2 plus 2 is 0. So this is the definition of a addition table, and similarly you can have the multiplication table. So please note that here, since you have zeros here, it tells you that there is one element for every element present which is an additive inverse, correct? All elements have an additive inverse. In fact, each element is its own additive inverse, and similarly you will find a 1 somewhere in every row and column except that of the 0, which tells you that there is a multiplicative inverse as well. So this is your GF4 or Galois field with 4 elements. It should be noted that in the addition we are not carrying out any modulo 4 addition. Only when GFQ, where Q is a prime number, will you find that the modular arithmetic works. Otherwise you have to construct the addition and the multiplication table, right? Also, it is interesting to note that Galois field for any Q will not exist. It will exist only for prime and prime power. So GF2 will exist, GF3 will exist, GF4 will exist, GF5 will exist, but GF6 will not exist, because 6 is neither a prime nor a power of a prime, whereas GF4 is 2 raised to power 2, hence a prime power. Again, G7 will exist, G8 will exist, G9 will exist, but G10 will not exist, right? So not all Galois fields for any arbitrary set number of elements may not exist. It has to be either a prime or a prime power. Let us look at another example. Let us talk about GF3. So there are 3 elements. Since 3 is a prime number, we actually have the modular arithmetic being valid here. So what we have here is the addition table and a multiplication table, and if we want to construct a simple code, right, which is a 2, 1 code, then we can have a set of elements defined like this. So we can have the 0 mapped to 0, 0, 1 mapped to 1, 2, and 2 mapped to 2, 1. All this mathematical detour was important to define another important subclass, as we said, of the linear block code called the cyclic codes. So cyclic codes is a special class of linear block codes with another constraint, another algebraic constraint. And please remember, the whole game in coding theory is to learn how to put more and more structure into your codes, because any break in the structure due to noise can be easily detected and corrected. So, a code C is cyclic if C is a linear code, and on top of that any cyclic shift of a code word is also a code word. That is, if the code word A0, A1, so and so forth, an minus 1 is in C, then if you do a cyclic shift, that is, you put the last element front and shift each one by 1. So, an minus 1, A0, A1, A2 up to an minus 2 is also in C. Any cyclic shift, shift by 1, shift by 2, any number of cyclic shifts will result in another vector which must also be a valid cyclic code word. Please understand that if this is true, if we can really construct cyclic codes, then they are very hardware friendly. We can generate them using shift register without any problems. So, let us look at an example. Consider the following binary code 0000, 0101, 1010 and 1111. They are block codes. The all 0 code word is a valid code word. You can check that sum of any two code words is also a valid code word. So, then it means that this is a linear code. The first property is satisfied. But next look at any cyclic shift. If you rotate this by 1, so put this 1 here and right shift each one of them, you get 1010, which is this one. If you right shift 1, again you get this one. If you do a cyclic shift of this, you get back this one. So, any cyclic shift gives you any one of the valid code words already present in the set. Hence, this is an example of a cyclic code. Fine. Now, let us look at a small example here, C2, which is 0000, 0110, 1001 and 1111 is not a cyclic code, because if you shift it here, you will get 1100, which is not already present in the set of code words. However, C2 is equivalent to the first code, right? Because all the distance properties are similar, but one is a valid cyclic code, the other one is not. Continuing with our mathematical detour, let us talk about polynomials, because we will soon see it is very easy and efficient to represent cyclic codes using polynomials. A polynomial is a mathematical expression. For example, f(x) is equal to f0 plus f1x plus f2x squared, so and so forth till fm x raised per m. So, it should be a superscript, where the symbols x is called the indeterminate and the coefficients f0, f1 up to fm are called the elements of GFQ. So, if I am going to define a polynomial over GFQ, then these coefficients of x must be taken from GFQ. If it is GF2 binary case, then f0, f1, fm should be 0 or 1. If it is from GF3, it should be 0, 1 or 2, and so on and so forth. The coefficient fm is called the leading coefficient, which belongs to the highest power x raised per m here. If fm is not equal to 0, then m is called the degree of the polynomial, and it is denoted by degree of fx. It is the highest power of x. A polynomial is called monic if its leading coefficients fm is unity. So, for example, this is a monic polynomial over GF8. Why is it over GF8? Please note all the coefficients belong to elements of GF8 0, 1, 2, 3, 4 up to 7, but the highest power is x raised to the power 6, it is a degree 6 polynomial, the coefficient is 1, hence it is called a monic polynomial. Let us talk about the division algorithm for polynomials. The division algorithm states that for every pair of polynomials ax and bx, where bx is not equal to 0 in the set of polynomials fx, there exists a unique pair of polynomials q x, the quotient, and r x, the remainder, such that a x is q x b x plus r x, where the degree of r x is less than the degree of b x. The remainder is sometimes also called the residue and is denoted by r b x a x. So, it means that you take the polynomial a x and you divide it by b x, you may get some remainder r x. That remainder is called the residue. It is like the long division that we have learnt in our school earlier. Two important properties of residues are residue a x plus b x is nothing but residue a x plus residue b x, and residue a x times b x is residue of the product of residues a x and residues b x. Here a x, b x and f x are polynomials over g f q. We will use these properties later on. Let us look at an example. We would like to divide this a x, which is x cubed plus x plus 1, by b x, which should be non-zero, x squared plus x plus 1, and we need a quotient and a remainder. Usually the remainder is the more interesting part. So, you carry out the basic division, which is the long division, and you finally obtain a residue. Thus, a x here is x plus 1 times b x plus x. This is all the division algorithm of the polynomial state. Please note that the degree of r x must be less than the degree of b x, which is 2. Fine. That is all there is to it. Now, let us do a couple of more definitions. It is worthwhile exploring the properties of f x which makes f x, capital F x by f x a field. So, what is this capital F square bracket x? It is a set of polynomials divided by f x, a field. So, this is again a set of elements, just like you have seen that earlier g f 2 has 0 and 1, g f 3 has 0, 1, 2 elements. You can have polynomials as the elements in the field. We would like to know when is this a field. A field, as you know, satisfied certain number of properties. We will find out shortly that the polynomial f x must be irreducible, that is non-factorizable, to make this a field. So, let us define a polynomial f x in capital F x, right, is said to be reducible if f x can be written as a product of two polynomials, that is, you can factorize it, where a x and b x are elements of f x, and degree of a x and degree of b x are both smaller than degree of f x. However, if you cannot do so, if f x is not reducible, it is called irreducible, and if f x is irreducible, then this becomes a field. A monic irreducible polynomial of degree at least 1 is called a prime polynomial. Okay? We will use this definition. Prime polynomials of every degree exist over every Galois field. A polynomial f x has a linear factor x minus 1, x minus a, if and only if f a is where a is a field element. A polynomial f x in f square bracket x of degree 2 or 3 over g f q is irreducible if and only if f a is not equal to 0 for all a's in g f q. And over any field we can write this following factorization: x n minus 1 is x minus 1 times x raised to the power n minus 1 plus x raised to the n minus 2, and so on and so forth till x plus 1. The second parameter, the second factor may be further factorized. Let us look at an example of factorizing x cube minus 1 over g f 2. So, clearly you can write x cubed minus 1 as x minus 1 times x squared plus x plus 1. This factorization is true over any field, but please note as we proceed further, if you try to factorize x cubed minus 1 over g f 2, you may not end up with the same result if you factorize x cubed minus 1 over g f 3. So, continuing over g f 2, let us try to factorize this term x squared plus x plus 1. First substitute 0 because we have only 2 elements. So, I am trying to see whether there is an x minus 1 factor or not, or x minus 0 factor or not. So, if you substitute 0, you do not end up with a 0. So, clearly x minus 0 is not a factor. If you put 1, again you do not end up with a 0. So, clearly x minus 1 is not a factor, right. Therefore, Px cannot be factorized further over g f 2. So, the best you can do is to say over g f 2, that is for the binary case, x cubed minus 1 is nothing but x minus 1 times x squared plus x plus 1. Okay. So, this is irreducible. We need irreducible polynomials which are monic and hence prime polynomials to do other interesting things for cyclic codes. Now, consider the same thing of factorizing x cubed minus 1 over g f 3. Again, you can, with your eyes closed, you can write x cubed minus 1 is x minus 1 times x squared plus x plus 1. Again, try to substitute p 0, 1. So, x is not a factor. Put p 1. Now, this addition has been carried over g f 3. Here, additions were carried over g f 2. Addition tables in g f 2 and g f 3 are different, and hence you x minus 1 should be a factor. Again, if you substitute 2, you do not get x minus 2 as a factor. So, we can conclude that if p 1 is 0, p is defined here, x minus 1 must be a factor. So, you can write g f over g f 3 x cubed minus 1 is x minus 1 times x minus 1 times x minus 1. So, clearly the term x squared plus x plus 1 is irreducible, that is non-factorizable over g f 2, but easily factorizable over g f 3. It is important to know over which field are you working. We will learn to construct codes over specific Galois fields. So, now we have a very nice way to construct Galois fields if we know that if f x is irreducible, if it is a prime polynomial. So, the ring f x over f x is a field if and only if this denominator is a prime polynomial in f of x. What is f square bracket x? Is a set of polynomials. So, we now have an elegant mechanism of generating Galois fields. If we can identify a prime polynomial of degree n over g f q, we can construct a Galois field with q raised by n elements. So, the job is to identify the prime polynomial. Such a field will have polynomials as the elements of the field. These polynomials will be defined over g f q and consist of all polynomials of degree less than n. It can be seen that there will be q raised by n such polynomials which form the elements of the field. So, how do we relate all this to cyclic codes? Having developed the necessary mathematical tools, we now resume our study of cyclic codes. We now fix f x is equal to x raised by n minus 1 for the remainder of the talk. So, we denote f x by R n, but we make the following observations. First of all, x n is equal to 1 provided you take modulo x n minus 1. Hence, any polynomial modulo x n minus 1 can be reduced simply by replacing x n by 1, x n plus 1 by x, and so on. This is an important observation. It means that if you are multiplying any polynomial by x n, right, you are effectively multiplying it by 1. A code word can be uniquely represented by a polynomial. So, here is the missing link. Why are we trying to study polynomials in coding theory? Because what we do is any code word can be represented uniquely by a polynomial, because what is a code word? It is a sequence of elements. We can put this sequence of elements as coefficients of the polynomial. So, there is a one-to-one correspondence. So, we can use a polynomial to represent the locations and the values of all the elements in the code word. For example, the code word C1, C2 up to Cn can be represented by the polynomial C0 plus C1x plus C2x square up to Cnxn. So, C1, C2 correspondingly form the coefficients of x, x squared, and so on and so forth. So, there is a one-to-one correspondence. But please note, if we multiply this by x, all we do is raise the power of x by 1. So, effectively we are shifting the elements to the left, but we must ensure that the number of elements do not exceed the block length. So, we must do a modulo operation to bring back the highest power back to n minus 1, and therefore, we have to carry out the modulo x raised to n minus 1 operation. So, here is another example where a code word can be represented with polynomials. Here again we have represented, if you multiply Cx by x, you just shift the polynomials. So, there are certain theorems for cyclic codes that we would like to take up in the subsequent lectures, that it is possible to represent cyclic codes by using polynomials defined using a modulo operations, and this will be the starting point for next lectures. So, generation of cyclic codes will also be studied in the subsequent lectures, where it is very easy to define cyclic codes based on the polynomials f(x) defined over Rn. So, let us summarize today's lecture. We started off with a brief study of linear block codes. We then talked about Galois field theory, and then linked it back to how to work with cyclic codes. We have just had a brief glimpse of cyclic codes. In the next lecture, we will start with cyclic codes and look at certain applications for wireless communications. Thank you.